I've got a whole bunch of slides about how to use Niagara, but since we're a fairly small group, we can go quicker or slower if you want. Just ask questions as we go along. That's fine. So there's really three main parts. You guys might know already, but I'll talk a little bit about SciNet is, and then we'll talk about Niagara and how to use it. That'll be the main part. And then a few tips at the end about data management and stuff like that. Oh, that's a lot of text. Okay, so SciNet, that's us here. We're a consortium of the University of Toronto and the hospitals that are in Toronto, most of them anyway, the research hospitals. And we do two things, or well, a couple of things, but two main things. One is we maintain and run large supercomputers for people to run on, and the other part is that we support those by training, like in sessions like this, and by answering emails. And so we're not the only, and we maintain those systems and we do that support for any researchers in Canada. So all of the large supercomputers in Canada for academic research are sort of pulled together, they're shared. And if you need a specific kind, even if it's not located near your local consortium, you can still use it. So the other systems that are in Canada that are run by other consortia like SharkNet, Hopeful Quebec, WestGrid, AceNet, and CAC in Kingston run other systems. For instance, there are some cloud systems that people use to mostly run things like web portals, or not really high-end computing, but more of a portal kind of thing. And there's a couple of general purpose clusters which have, which one of them is in the west at Simon Fraser, one is at Waterloo, so not too far, Graham, and the new one will become operational next year. It's called Beluga. It's in Quebec. Those three are all general purpose, which means that pretty much anyone can run whether they need a lot of parallelization or have a whole bunch of small jobs. Doesn't really matter. Niagara, which we host here in Toronto, is aimed at large parallel computing, and we'll see a few things in the setup of the system that show that. So the idea is if you have either a lot of cases can run in parallel, or one large simulation that has to run on more than one node because one node doesn't have enough memory to hold the whole system. Stuff like that should run well on Niagara. So, as I said, we host computers. Niagara is currently our largest and most powerful one. It's also currently the largest academic one in Canada. We have a second one that is in core count similar, but in performance a little bit less because it's a little old in the tooth. It's the Blue Gene. They're very different machines. You're going to be running on Niagara. You won't be using the Blue Gene because the Blue Gene is part of a special platform called SOCIP, for which you have to have an industrial partner within South Ontario, I believe. But I'm saying that because we run both, and that keeps us busy. And then we have a bunch of smaller ones with some power systems. I'm not sure if you still have the KNL running. We have a GPU resource, which is also part of SOCIP. And so let's look at Niagara in specific. Okay, we'll look at Niagara specifically. So the other thing we do is training. It's a big component. This is one of them. We give courses on scientific and parallel programming. Quite a few of our training courses are now in the form of graduate courses. So you can take, I don't know if anybody is taking these, I think you have. Courses on scientific computing for physics, data science, and biostatistics in combination with the Institute for Medical Science. Usually you can still attend those if you're just a user, just sit in, but you might not get credit. Data management, parallel IO. We also do a summer school together with the other Ontario consortia every year, 3 streams, and we're involved in the international summer school as well, which this year will be in Japan. So that's interesting. All our courses have a website where I hope you sign up, courses.scinet.gibraltar.ca. A lot of them are recorded. Some of them are broadcast if it makes sense and if there's demand. But if you want to get some credit for them, so it can be two ways, either because it's a grad course and you just get credit, or because you take many of these courses. If you take 36 hours worth of courses, SciNet will issue a certificate for you. And I can talk about the different kinds we have, but for that you kind of have to be either present or it has to be a course where there's active grading, as otherwise it doesn't make sense. And then we do a little bit of research too, and I've got a link there. And that's the training, because we find that training is a good way to help users sort of preemptively. If you still need help, there's a wiki. The quick start it contains most of the stuff that I'm going over today. It's hosted at our wiki, but also at the Computer Canada wiki. If you need support, you can write to the old support at SciNet or to the newer Niagara at computercanada.ca. The same group of people sees it. Actually, Niagara Computer Canada might have a few more eyes on it. And if you still need help after that, you can always ask a one-to-one consultation. So you just write to support at SciNet, and then you say, hey, could I come by and talk about my project? See what we can. So don't be afraid, we're here to help. This is us. It's a relatively small group. So kind of artificially divided into the people doing software, user support and training, where I'm there, and people taking care of the hardware and the systems. There's some mix here. Most of these people have a scientific background. The vast majority has PhDs. Some of them have been postdocs, so they kind of know the struggles that you're going through. And so they're excellent people to ask questions to. With our CTO, scientific director, business manager, and if you came in through the front door, you've seen Alex sitting there. So a fairly small group, because we have hundreds of users, but that makes a smooth dynamic. Okay, so the thing you really came for, this is Niagara, and it's pretty big. It has 60,000 cores. These cores are not so much divided as they come in bunches of 40 cores in a single node, and then we have 1,500 of those, so that makes up 60,000. So that one node is kind of like an individual computer, but just a very, very multi-core computer of 40 cores. You'll see this pop up, but although there's 40 cores in one of these nodes, the operating system sort of presents there's 80, and there's some benefit to that, but at the end of the day, you really have 40 things doing work. So, we became operational in April of this year, which was good because it meant we could get onto a ranking list of the top 500 fastest supercomputers in the world, or at least supercomputers that people make public. And so we're number 53 in this list. It's pretty nice to be in the top 100. What else? Okay, so we have 40 cores. You have quite a bit of RAM in each node, but with so many cores, that amounts to about 4 gigabytes per core. It's running Linux, as almost any supercomputer runs. One of the things that sets it apart from, say, the general purpose machines, because this could be general purpose as well, is the interconnect, so the network. If you want to run things in parallel and they have to communicate, you want to do that quickly. You don't want to wait for this. And so we have a very fast interconnect that's called InfiniBand, and that in a specific topology called Dragonfly Plus. If you're interested, I'm happy to talk about it, but for all intents and purposes, it's just fast. So that's good. Another thing that is kind of peculiar, but part of this idea of being a large parallel machine, is that there's no GPUs and no local disks. So local disk would be useful if you're running something on a node and you write to that disk. But if you're running on multiple nodes and you write to one disk, then the other node doesn't see that disk. So it doesn't really make all that much sense. Instead, we have a large parallel shared file system. And so with the cost savings of getting rid of the disks, we bought more nodes. just makes it bigger. And the no GPUs is kind of peculiar because a lot of modern supercomputers come with GPUs. We actually asked our users of the GPC and the TCS or our previous machines, what are you running and can you use GPUs to run your large cases? And some of them said yes, but most of them said no, we'd rather have a lot of CPUs. And so we said, okay, well, if that's what you need, yes, that's what we'll give you. If you need GPUs, if you have a workflow that uses that, use that efficiently, they have lots of them at Cedar and Graham, and they'll have even more in Beluga. So there's places to do that kind of work, and there's nothing wrong with that. But Niagara is completely homogeneous, at least as it stands today.
So is GPUs mostly for people who want to visualize their data?
No, you'd think so, but a lot of people use GPUs to compute, because basically they're highly parallel machines, but they can only do very simple sort of lockstep calculations. So the idea of GPU is basically think of it as generating the pixels on your screen. What it has to do for each pixel is essentially the same. It has to do it many, many times. So it's very good at arithmetic, but what it isn't very good at is logic. So if there's a lot of different cases or if statements or that kind of stuff, doesn't naturally fit into the GPU realm. So people use GPUs a lot for machine learning, where and basically because machine learning is at the heart often linear algebra, and linear algebra is doing the same thing for lots of matrix elements. So you can kind of see how that works. Or for molecular dynamics simulations, mostly because there are packages that have already ported to GPUs, so it's just ready for you. Those are the main, and then there's always some people writing GPU codes themselves, but those are big use cases. If you're doing R or Python or that kind of stuff, there are packages to link with GPUs, but you're essentially still programming for a GPU. So if you just already have a workflow that is based off of that, it's going to be tough to make it work on a GPU, without reprogramming. Okay, so that's the system. It's a shared system, obviously, so there'll be some way of having a few hundred users on there and using it fairly, but efficiently, etc. So, so that's brings us to the next point. How do we use this? Any questions on who we are and what the systems are? Have you guys worked with Linux before? No. Okay. There's some Linux courses coming up as well, so you should probably take them or look at the videos if you want. Yeah. Okay, so getting into the system is number one. If you have a Computer Canada account, that is in principle all you need. All of the logins for all of the supercomputers are the same with the same password and the same login, except that for Niagara you do have to request access. That is helpful for a couple of reasons, but if for nothing else, just so that there's a home directory for you and the scheduler knows who you are. So you have to go to the CCDB site and get a SciNet account. Still called that way, although it really just gives you access to Niagara. It takes a couple of days. If you've not done that yet, it's not difficult. And then you can log in with your CC username. So if you've used the GPC or TCS before, there was a separate SciNet account as well. You might have had a different username. You probably would have had a different password there. For Niagara, you use the Computer Canada passwords and usernames. So either go to niagara.scinet.utoronto.ca or niagara.computercanada.ca. They both work. We got the first one up first, and then we said that it makes sense to have it in the Computer Canada family. And now we can't switch one of them off because people use both. So whatever you prefer. So that gets you to login nodes of Niagara. So Niagara has these 1,500 nodes, right? But then we have 6 other nodes that are sort of separate of it that we call login nodes. They are the same architecture. They have slightly less cores and slightly less memory, but it doesn't really matter because they're not meant to run things on. They're meant to prepare your jobs in or compile your code or test out things a little bit. So you get to those login nodes first, and those are shared. So there's a few dozen people on each of the 6 nodes typically, and so that's where you sort of prepare your work. And so you get there by SSHing. So SSH is secure shell. If you're on Windows, MobaXterm is a very simple way to get SSH. If you're on Linux or Mac, there probably already is a command called SSH, and otherwise it's easy to get. It's all command line based. This is another thing that's typical of supercomputers. There's no GUI. GUIs are a little slow. If you do want graphics and you have you have an X server running on your own machine, you can use the -y and then you can pop up windows, but that's optional. It's not really essential. Okay, so that is the login nodes, but there's only 6 of them, and there's hundreds of users, and they all start running on those 6 nodes. Something goes wrong. It becomes very slow, and we're not using the 1500 real compute nodes. So the other 1500 nodes are called compute nodes, and you don't log into them directly. You request for a piece of computation to run on one or more of those nodes through a scheduler. So the scheduler is the piece of software that makes sure that this resource is fairly shared. And so you submit what's called a batch job. It goes into a queue. At some point, there's some room in the system for your job, and it runs it for you. That's the so it's not interactive for sort of production computations. On the system, you have a couple of directories where you can put your stuff. There's a home directory and a scratch directory, and these are encoded in environment variables. So environment variables, if you've not worked with Linux, typically start with a $sign, and they're set for you. So you can, once you're on a prompt, once you've logged in, you get a prompt that kind of looks like that. You can ask where you are. pwd is the command that says present working directory, and that, when you've just logged in, will be your home directory. So it's kind of long. That's why it's in an environment variable as well. Just use $home if you're ever lost, and you will find your way home. There's a second directory that you have access to called your scratch directory, and that's in $scratch, and it kind of looks the same except it starts with scratch. And the reason that there's 2, it will become clear in a little while, but scratch is a large, you have a lot of space in scratch, but it's neither backed up nor should you keep things there for very long. So it's really, as the name sort of implies. Then if you could have more directories if you have what's called an allocation. So if you've just gotten your account, you get access, you can run things, that's fine. But there's lots of users there, and it's hard to make sure that important projects get done if we just let anybody submit and it's just first in, first out. So there's an annual allocation round where people say, I would like to have this much time on Niagara, or this much time on Cedar, or this much time on Graham. And they have to write a proposal. It's called the REC allocation round, and Compute Canada sort of steers that. So you'd submit a proposal, or in fact your PI or a delegate of your PI would, your supervisor would do that and say, I want this much this space, this much that space. Now there's this round is just started. I think early next month is the deadline, so this is a good time to figure this out. Usually people try things out to get an idea of how much do you need. There is a reasonable amount of stuff you can get done with a default account, so without an allocation, but it's limited, right? And you're fighting for the leftovers, more or less.
I have a question.
Sure.
So without this RAC allocation, we're only allowed 12 hours to do the.
Yes.
Yeah. So.
With the allocation, it only goes up to 24.
Oh, it's not like we used to have 48 hours.
Yeah.
No, so the 48 hours are gone, and this is one of the. I have a slide on the exact limits, but there are limits on time and limits on the number of nodes. The limits on time really have to do with the fact that we actually have less nodes and we schedule them per node. So to get large jobs scheduled, we need fast turnover of nodes. And so that's why we went down from the previous 48-hour limit to the 24-hour limit for allocated users. And just to make sure that default users get something done, we want even faster turnover for that portion. And so they get 12 hours. And yeah, without that, large portions of the system would be, okay, so imagine we're trying to run a 1,000 node job, right, for 24 hours. Well, other jobs are running. If they're running for 48 hours, on average, half of those 1,000 nodes, 500 nodes, aren't doing anything for a day because they're just kept until that job can run. And that would really be inefficient, right? It would just be wasting energy and other people aren't running. So it's really to promote the turnover. And I know that can make it harder to set up your computation because you have to do some restart and make sure that works. Restart is a good idea anyway, because it's kind of, once you have it, you kind of have insurance, right? There's an unfortunate power failure, you have at most lost half a day's work. So that's not bad, right? I mean, it's bad, but it's, whereas otherwise you'd lose 2 days. And some of the other systems have longer times. So if you really have a few very long running computations, you can run them on Graham and Cedar. You might be waiting for a long time in the queue before it will give you that, but you can. So, but having lots of computations and having them take long just doesn't really fit well in the scheduler.
So besides this RAC allocation, do other people, like if we submit, say, in our group, we have, whenever we submit jobs, people are saying that if we put, like, there's a group kind of identification at the end of the job we submit, it increase pulls up our priority. So this is something different from the RAC allocation.
No, it is in a sense. So most people only have access to either the default account, as we call it, or a rec account.
Oh,
and in that case, at least on Niagara, it sort of picks that automatically.
Yeah.
But a few people might be associated to multiple projects.
Okay.
And then choosing the right project can make a lot of difference, because if you choose a project that is just a default project, yes, your priority is going to be fairly low and you wait a long time. And if you specify, oh, it needs to be part of this rack allocation, then so it only really matters, or only can help you if you have access to both, and your default is or the default choice, if you specify nothing, is the low priority one.
Okay.
Most cases, the accounts are created such that if you have access to a rack allocation, that will be your default. But if you have 3 and 2 of them are, like, they're complicated cases sometimes where you have to be specific. And so, yeah.
Okay.
Yeah. Usually you don't have to worry about that. We've tried to automate that right? But
there is one time I waited for a day to.
Oh, that can happen. Oh, the usage fluctuates a lot, right? And we typically have like 3 times as many cores requested, or 4 times as many cores requested as there actually are.
Right.
But and we could talk about the fair share more later. But the more people run, the lower their priority is. So these people might have submitted 1,000 jobs, but they're not going to get it run until weeks later, because their priority is so low. So your job submission doesn't go to the end of the queue. If this is your first job, it'll go fairly quickly because you still have priority left, so to speak.
I see. Oh, okay. So the more jobs you run, the lower priority you get for your next job.
That's right.
So, okay.
Yeah. So the idea is that you get a share of the time, if you want to. It's almost a time share. Once you've sort of used that up, your priority goes down. If there's an opportunity for your job to run, it will run it. Like if it fits in a hole in the schedule, it would do that. But no. But yeah, the priority is down. But then it only does that for a fixed time period. So after about a week, the cost of that priority, I think, is slashed in half. So it only counts in half, and then a week later, it's all gone. So you can't really use up your time for the whole year or something like that. But you can use up your time for that week, and you're pretty much like effectively you're done, unless nobody else runs, and then you still get it.
So the RAC is for requesting like 24-hour blocks?
No. So you request core hours or core years, I think. So you kind of have to do the total sum of, okay, how long do I have to compute and how many cores do I need? And then sum it all up, and that's your amount. And you indicate if they're parallel jobs or not. You even indicate what system you want to run on. So if you're running serial jobs, it might run better on Graham and Cedar. If you're running parallel jobs, you probably want to run it here. If you need GPUs, you cannot run it in Niagara. So it's actually, with just having 4 or 5 systems, it's a fairly easy choice. And choosing between the general purpose ones like Cedar, Graham, is usually just done out of convenience. Which one are you closest to? It makes no sense because you log in remotely anyway, but just as a default.
Okay, so like how long do you have this project allocation for?
So you have it for a year.
Okay.
And then if that allocation, if that's still okay with you, your groups in the next year get a fast track, and they say, okay, nothing has changed, I want the same thing again. And you can do that 2 times, so you can basically have 1 application for 3 sort of easy years, and then you have to apply again. If you want to increase anything or change anything, it's a new application again. But the application is really, you should, I can point or put some links on the website to where you go, but it's not meant to be a redo of an answer application. It's really meant, you have to say what the science is, and that will motivate how much computation you need. But it's not supposed to judge if that's like the most important science. Is it scientifically sound, and do the numbers sort of add up? That's kind of what it goes. Then it goes through a committee, they rank it. You typically get a percentage of what you ask for, because there's always more ask than there is supply.
So do you get parity, or you're like your own node or something?
No, so it's all priority based.
Oh, okay.
And so that's good and bad. It means that if you wait for until the last week of the year to do all your computations, there's no way you can get all that time. There just isn't, right? But it also means that if you happen to run a lot in the first month, you're not done for the year. You can still compute. So the design is such that if you were to submit constantly throughout the year, you would get that amount of time. Like that's how it works out. But it doesn't by priorities. So the priorities are weights in the scheduler that, in a uniform case, give you that amount of time. So in the end, you really get a percentage of the time rather than anything else.
Okay, and you get that priority for however much time you requested, and then.
Well, you get it for the year, so you always request for a year.
Yeah, but I mean, like if you used up all the memory or cores or.
Oh, it doesn't matter. After a week, you're basically back.
Okay,
or weekend, and so the half-life, I think, is a week. The schedule works a little funny.
Oh.
Yeah.
Okay.
Okay. Yeah, and the nice thing is if you do have a rec allocation, so if you need less than, say, 50 core years, they tend to say, well, no, you don't have to bother asking for it. Just use the default account. If you can't get it on Niagara, just get a little bit more done on Cedar and Graham, and you'll manage, right? That's sort of the cutoff. But if you need a lot of storage, then that cutoff for compute doesn't really matter. So if you need 100 terabytes of live data, and again, that goes into that same ask. And that would probably go into what are those project directories. So when you have an allocation, you can get project space, and the nice thing about project space is that it's backed up. So Scratch is not, which is good if you're just working on it, and you can regenerate and you can copy it off if it's not too much. That shouldn't be a big deal. But if you have big data that is supposed to be live and present for the whole year, the project is nice. Unfortunately, we can't give project to everybody. Graham and Cedar can, but only to a limit. The max is 10 terabytes for defaults on Graham and Cedar. On Niagara, the default is 0 project for non-allocated users. We give the odd 1 or 2 terabytes here and there for people that can use it, but just at a ad hoc basis.
Do people have different priorities with different rack allocations, or is it all the same?
Yeah, that can happen, except as a group, you can only request, so as a PI, you can only request 1 allocation. So it's not really project-based so much as group-based.
Okay.
So they call it research, or the resources for research groups.
Yeah.
That being said, some people are clever and they have 2 PIs and then they become part of each other's group.
Okay.
It's not the rule, but then anyway, any PI can just get one what they call an RRG, and then for these cloud stuff, they can get a separate one for that. And yeah, that's it. So we have project. Project is in dollar project if you have. If you don't have project, the dollar project will say something cryptic like / you don't have a project directory / something like that. So at least you know that it doesn't exist. Use these environment variables because suppose you change group or you become your own PI, then these paths will change and your scripts won't work anymore if you use the absolute paths. But if you use the $scratch, $home, and $project variables, they will still work. Right, so here's some of the limits on the storage. Home is not small. You have 100 gigabytes. That's pretty nice. The idea is that it's probably where your code goes, where scripts go. If your data is sort of static, so you just read from it and it fits in there, that you can put it in there. It's backed up, and you can see it on login nodes at computer nodes. So all of these directories are in a shared file system that is visible on all the nodes. You never have to transfer files from one node to the other. They're already there, they're shared. Scratch, you have a much larger quota, 52 terabytes, but it expires after a few months. So anything that isn't used in 2 months is deleted. You'll get an email with a list, or they point you to the list of files that will get deleted. You get that 2 months ahead, 2 weeks ahead of time, and then another 3 days ahead of time. So you can take action if you didn't want these deleted. And it's not backed up. It's really meant for live data. Now, if you might think, well, I want everything backed up, and the truth is we don't really have enough tape drives and tapes to do that with so many terabytes. So it would be too costly. You'd have much less space. Project is kind of a Scratch that's backed up. There's no expiration time. It is backed up. Right, and then there's 2 more that we have at Niagara. Archive, which isn't sort of a live directory, but it lives on what's called HPSS. It's an archive system. So if you have a lot of data, even if it's just on Scratch, and you go, well, I'm not using it for the next 4 or 5 months, but I'll need it later, you can put it in HPSS. Just ask us, hey, can we get access to HPSS? We'll give you a terabyte or 2, and you can start transferring things. So it's slower, obviously, because you'd have to reclaim it when you need it. But it's safe. It's I wouldn't say backed up, but it has 2 copies. So there's actually 2 tapes with your data on it. We have yet to lose anything from there. So that's archive, and then there's a 5th one, burst buffer, which is sort of a fast Scratch, like a super fast Scratch. So Scratch is good. It's fairly fast for large files. But it's not very fast for lots of rapid I/Os. If you have lots of little files that you create or you read little things. So we have a smaller shared file system called burst buffer that is for that. And really it is yet another file system, but it's designed to be higher performance. And we would make everything that high performance, except that system would become too small. So we have a big Scratch that is okay performing, and a sort of small burst buffer that is really fast. Okay, so again, you just have to ask for it, but you can get about 10 terabytes, and then you can just, if you know that your application is really heavy on I/O and is stuck most of the time reading and writing from disk and not so much computing, switching to burst buffer can make a big difference. So it's an even faster Scratch. So the idea is your job is writing like crazy. But at the end of the day, you have some data set left. You copy it out of burst buffer and put it back in your project or your Scratch just once after that. So things shouldn't live very long in the burst buffer. Now, burst buffer is something kind of new. So We're still sort of figuring out what the best policies are, but that is sort of the idea behind it. It's not backed up. It's kind of a super scratch. Think of it like that. There's one more thing that's very important in this set of directories, is that your home directory is read-only on the compute node. So when you're running your batch jobs, you cannot write to home. That sounds odd. It is a little bit odd. The idea is it's sort of a protection of your own data. If you had a few dozen jobs and they accidentally all start overwriting things in your home directory, even if it is backed up, that's going to be messy. So your home is precious. You keep it. You do your work on scratch, and then once your job is done, you can copy it back over to home, or maybe it's just fine on scratch until the next job comes along. Right? So figuring this out can take some thinking. It's not just one big disk. It would be great if we could have one big disk that is fast performing and constantly backed up. It's not the reality of things. There's this tiered approach, and we kind of have to work with this. Okay, so that's the start. Moving data is actually simpler than it seems. You can scopy, so there's an SSH command to log in, there's an scopy command to copy things over. You either go directly through niagara.computer.canada.ca, that works well until you hit about 10 gigabytes per transfer. Anything larger, you want to use the data movers because they're faster and they have a better connection. And the only difference is really the address you use NIA data mover 1 or NIA data mover 2. Pretty simple. Actually, yeah. So we've changed this a little bit. It used to be difficult to get things from the data movers. You have to go log into the data movers and pull your data from somewhere else. So this last line is no longer true. All that you need to do is use this address instead of just Niagara. HPSS has its own funny interface that I won't go into now. It's not difficult, it's just different. There's some commands that you have to use to copy things over. You put those in a script, you give the script to the scheduler, and that's how it goes. Conceptually not difficult, syntactically you figure it out once. So it's our archive. It's also something called nearline. It's allocated through the rack allocation, so you can get tons of space on there, and it's cheaper space in a sense than project. So that's good if you have data that needs to live there. You can get small amounts, and by small I mean a few terabytes, just by requesting it as well. So we'd rather have data live on that is not used lived on tapes that doesn't take any electricity to run than on spinning disks where we pay for every byte that's stored per second, right, essentially. Okay, so that's the storage. Good, your stuff is there. You have space. Now you want to do something with this stuff. So you want to use some software. This is very similar if you've ever run on a supercomputer or run the GPC. We use the module system to coordinate this, and the thing that the module system solves is that we have many users, they all need different software, and that software sometimes conflicts or has different versions, and you can't have them installed at the same time. Having modules solves that. So they are all installed, or a lot of them are installed, but the system doesn't see them until you load a module. And so you can load different modules. If you do modulespider, you'll get a list of all of the modules in alphabetical order. So you can already, this is a long list, but you can already see on the top of them there's different versions of Anaconda, there's different versions of CMake. So you need CMake 10.2, fine. You need CMake 3.10.3, fine, they have that too. You can be very specific on the version numbers, and they don't bite each other because of that. So there's some commands to know. If you want to load a module that you see in that list, you do module load. If you want to unload all of your modules, module purge. If you want to look for a module, the command is called modulespider. It's an odd name for something that just searches, but that's what it's called. Module avail is a little bit strange. We'll look at it in a second. And module list lists what you have currently. So those are the commands, or the main commands that you do. But what you're going to do is you're going to figure out what modules you want. You're going to module load those. You're going to put that in a little script, and then whenever you start, you just run that script. Or if it's just one module, you just type module load r/3.6 or whatever, something like that. Now, different from the other compute kind of systems, there's two software stacks on Niagara. There's a sort of native one that SciNet has built that is optimized for Niagara. You have that by default, and so that's kind of the one that you probably want to start with. But if you already have a workflow from Graham or Cedar, we have all of that stack available on Niagara too. And all you have to do is sort of switch stacks. And you switch stacks to the compute kind of stacks by doing module load, CCNV or standard env. So this software stack isn't particularly optimized for the chips that we have in Niagara. It would probably still run fine, but that's how it is. The standard env here, well, that's not a difference between the other machines and Niagara, loads a whole bunch of modules for you. So CCNV is enough in principle, but doesn't load anything. So by default, when you log into Niagara, you have no modules loaded at all. There's no compiler. There's a ridiculously old version of Python. There's no R. You have to load modules to do anything. We do that on purpose because we found, looking at the old systems, that people eventually need different modules as they go through their life on the supercomputer. And if you load defaults a priori, then at some point they're going to load something else and it conflicts with it. And now we have to go through hoops to make sure that the old modules aren't loaded. If you ever have two projects that run at the same time and they have to have, one has to use an old compiler and the other has to use a new one, having defaults just sort of gets in the way. So you can make your own defaults if you want, but we haven't set anything up. But on Graham and Cedar being sort of general purpose and trying to make sort of easier entrance, they have a compiler loaded. I think there's a Python loaded. There's an MPI compiler loaded in this standard env. So that's why you have to. Yeah, sure.
So for the Niagara system, before we load any specific modules, do we have to load this Niagara?
No, so that's there by default.
Oh, okay.
Yeah,
So
yeah. But if you had loaded this one to get back to the Niagara, and you'd have to do module load
I
and
see.
so it's really to get back. I should have them in the opposite order, but yeah.
What does the Nia env contain?
Nothing, but it points at the directory where all the Niagara optimized modules are. So really just all those modules are stored somewhere, and there's a set of modules for the Nia env and a set of modules for the CC env, and there are different directories, and all this does is really say, use this directory for your modules or use that directory for the modules.
Okay, so if I log into the general purpose clusters, that's going to be downloaded by default?
Yeah, so there won't be a Nia env yet. Yeah, so this will be by default. So if you log into Cedar or Graham, if you type module list, just after you've logged in, you'll see, you won't see CCNV because that's our tweak to switch, but you'll see std-env, you'll see an Intel compiler, you'll see an MPI, you'll see all of these things in your environment already. And if you want to get rid of them, you have to do module purge. So, whereas in Niagara, you don't have anything, you have to do some modules, but you don't have to module purge.
So if someone is using software that runs on an old computer, that's why they would download CCN on Niagara?
Yes, yeah.
Okay.
If I did module purge in Niagara system, I wouldn't be able to purge the Niagara.
No, so it protects you against that. So module purge will get rid of anything except Nia env, and in this case, it will get rid of anything except CCNV and std-env. And that's because it inherits that same mechanism from Cedar and Graham, where you can't unload the std-env unless you say module -- force purge, and then you can get rid of std-env. But yeah, it's getting a little detailed, but yeah. As I said, mostly you're going to figure out which modules serve you and just use them. So it's yeah. What else? Okay, don't put them in your bash RC, the module loads, because they become defaults. It would work, but at some point you're going to change your modules and change your minds. And then you're going to change your bash RC. Your old scripts don't work anymore, or you didn't change your bash RC, and your new scripts aren't working. So it gets confusing.
What is the bashrc?
Oh, so the bashrc is a special file in your home directory. It's actually a dot in front of it, dot bashrc. The dot makes it hidden, so if you do an ls, if you list the content, you don't see it, but you can edit it. You just say vi or nano or emacs dot bashrc, and it contains commands that are run the first time you log in. So it would be the place where you would automate things like loading modules. If you know that forever you will always need only those modules and you'll never switch, if that was true, then you would put them in your bashrc. You can put aliases in there, special functions you have. You can append paths to your own directories and stuff like that goes into bashrc.
Like the definition of home and scratch is in bashrc?
No, those are done on the system level. Yeah.
So there's only one bashrc in your home?
Yes. Yeah. Yeah. Another reason why we used to not do this is that the same bashrc will be used on different systems, but the modules aren't the same. So that is highly confusing too. We don't have that at the moment. There's some abbreviations of the module command. Module this is ML, module ML and the name is module load, and ML anything else is also module, but you can just stick to modules. Default versions exist too. So sometimes we have several versions of a package. Like for the Intel compiler, I think we have Intel 2018.2 and .3, etc. You can just type module load Intel, and you get whatever is the default, and that will work. But if you're doing this in a job script, if you're doing this in jobs, you want to be specific with the version, because in 6 months you'll go back. The referee asked for your paper, can you rerun this? And you want to rerun it with exactly the same compiler. If we've changed defaults, then something might change. Right? It shouldn't, but it might. So just for your own record, just be specific. It's better. Spider. So let's look at what Spider does, module Spider. So if I'm trying to load some module like OpenMPI, and this module command actually is a specific version of module commands called lmod. So you'll see lmod has detected an error. And it's figured out that this module exists, but it won't load it. It also won't tell you why it doesn't want you to load it, but it gives you a hint as to how to figure that out. Try module spider and OpenMPI. So the spider was the sort of the search facility. Oh, I'm going the wrong way. The search facility. So if I do module spider OpenMPI, now it's going to search for OpenMPI versions. And so it'll find 3 here. It still doesn't quite tell you how to get them loaded, but it says that they exist. But if you want to know how to load it, it says, well, you can try module spidering the exact module. And if you do that, so the exact module, it'll tell you, okay, it exists. And then if you want to load it, you have to load either one of these lines. So nia-env, which is already loaded, so you don't have to load it again, and GCC 7.3, or nia-env and Intel 2018. And so you would do that. You probably just cut and paste, module load these guys, and then you can module load OpenMPI. So this is a dependency of the modules. The OpenMPI module needs an Intel compiler or a GCC compiler. They also need a nia-env, but it's already loaded. So that's just there because the module command says, hey, you should have it. You already have it. If you want to see or spider the modules from the CC stack, you first have to do module load CCN. Because those two modules sets are really separate. You can't mix and match them. It makes no sense to spider one and the other at the same time. So this, yeah, makes sense. All right. And then if I module list, I actually see that these things are loaded. Okay, commercial software. I don't know if you guys are running anything commercial. Yeah, it's possible, but we don't have licenses for any commercial software except for the compiler. So you kind of have to bring your own license or have a license server running somewhere. Talk to us. think we haven't found a case where it's not possible yet, as long as your license gives you permission to run on a cluster. Right? So it's more the license details, but there might be some hoops to go through to make sure that the license is checked properly and stuff like that. So it won't work out of the box, but it can be made to work, and we'll just help you with that. So ANSYS, MATLAB, Gaussian, those things. I think Gaussian we cannot run because of the license, but it can on Graham and Cedar. So
What about Simplex and Groby? The optimization software?
good question. We'd have to look at the license. Probably yes. Kurobi, I think we've gotten it to work before. Yeah, that rings a bell. So yeah, I think it should be fine. It just the first time you've set it up, you have to make sure that there's the right commands in the job script and stuff. Just send an email and we'll figure it out. Okay. Yeah. Okay, so just to show you sort of an example of a workload. Suppose you had code that you need to compile. What would be sort of the trajectory? You would log in. You would have nothing in your module list except the nia-env, and you load an Intel compiler, for instance. Usually you want to do Intel compilers. And say you needed a library, in this case a GSL library. You've loaded those, and you'd have to source files, these are C codes. You'd compile them. The Intel compiler has a C compiler called ICC. These happen to be the commands for it, and you could run it. If you're compiling your own stuff, make sure you have optimization switched on. So -O, this is O3, optimizes the code, and -X host, make sure that's optimized for this particular host or this particular architecture. Otherwise, it will compile for any old x86 architecture and not take advantage of the machine. This is if you're compiling your own stuff. Need this. One of the nice things of the setup here is that you don't, while these modules that are now loaded have the software in all kinds of non-standard directories, the way it's set up is we don't really have to specify those directories in the compilation anymore. On the GPC and the TCS, you had to add extra indications to the compiler saying, okay, my include files are here, my library files are there. We kind of did away with that and optimized it a little bit.
Can you explain the X-host again?
Yeah, so X-host is an optimization flag, and it says compile this code using instructions that this particular Intel chip has. And if you don't do it, it'll use only the instructions that the very generic broad set of Intel chips had, so that you could take that executable and copy it over to another machine and run it there. So if you were a developer and you want to distribute binary code, you do not want to use Xhost. But if you're compiling on the machine that you want to run on, you want to do Xhost. So you're going to miss out on optimizations if you don't.
Mm-hmm. So this is for like compiling C or C++?
C, C++, Fortran, yeah.
Okay.
Yeah. On like things like Python are hopefully already compiled with those flags.
Mm-hmm.
Right, so we've compiled it. The next step is not running 100 of these computations, but is to make sure that it runs. So just do a little test. You can run short things on the login node. So you've just compiled it, or maybe you just got a script from somewhere, you've loaded the Python module, and you want to run that script. Run it for a little while to make sure it launches properly, it does the stuff. If you can create a small test case that runs like a minute and takes just a few cores, that's good, right? Before you put it in the queue, and you'll have to wait for a few hours or maybe a day for it to run, and then to see that it doesn't work, that would be a waste. Now, you can do this on the login nodes at small scale, but the login nodes are shared, so we can't have you run big tests, and you can't trust the timings of your test either, because how fast things go depend on what other people are doing. But you can get, for a short period of time, you can get a compute node for yourself as if it's a login node, and we call those debug jobs. So you can request a number of nodes, n. Usually you start with n equals 1, and then you say debug node 1, and it basically creates a job for you on the compute node and then logs you in there. And so it's as if you've logged in there, But it's a compute node. You have the 40 cores to yourself. You have the 188 gigabytes for your own. Nobody else is on that node, so you can do testing. You get them for an hour. So especially if you want to figure out how long is my job going to take, you need realistic timings. You just ask it, and they're very quick to get. Like typically, we have only 5 nodes set aside for this, but people don't use them much. So usually there's 1 or 2 open, and you just it's as if you just logged in there. Okay. Yeah, and they are exactly a compute node. So home, you can write to home there. You have no limits on the size of your jobs. You have all the cores. You don't have internet access, and say that yet, but you can't have internet access from the compute node. So all the restrictions are there too. So it's a true test. Okay, so once you have your tests, you know what commands you want to run. But now you, of course, have several cases, because if you were done, you were done. You don't have to do this step. You need to submit jobs to the scheduler to make sure that this is all fairly shared. The algorithm that the scheduler uses to take your batch jobs and put them on compute nodes is actually called a fair share algorithm. So fair. The command, so you put those commands that you want to run in a job script, and in this example it's called job script, and then you use the sbatch command to give it to the batch scheduler. So doing that will put this job in the queue. This script has to contain parameters of resource parameters of the jobs too. So how many nodes do I need? How long do I need them for? And then the scheduler will look at those and try to fit you in. Eventually it will run, if you have a rack allocation, it will run using that priority. So RRG is the resources for research groups allocations. And if you don't have one, you have what is called a rapid access service allocation. It's just the default. It's just your account. That's a fancy name for it. You have less priority, but they'll use that. A few things to keep in mind. I've mentioned it already. We schedule by node. You can't get just a single core on a node. If that's the workflow you need, that's what the general purpose clusters are really good at. But the idea is this is for parallel jobs. If you can't run 40 things at the same time, I don't think you're big enough to be here. You don't need us, basically. So you get multiples of 30 cores. Please use them. You get a maximum wall time of 24 hours or 12 hours if you're a default user. Again, this is really for turnover, so that those big jobs have a chance to run. It actually helps in getting default usage going too, because the system isn't locked up for 2 days and you don't get anything done. So it does help in availability, but you sometimes have to work around that limitation. You have to write to Scratch or project, because home is read-only. That often means that you want to start your sbatch command from your Scratch directory. There's ways to do it so you don't have to, but by default, your output of your job gets written to the directory that you submit from, but if you submit from home and you can't write to it, basically your output is gone. And the other thing, oh yeah, I did mention this, compute nodes have no internet access. So if you need to download data, you can't do it while you're running. You have to download it first from when you're on the login node, and then use it in your job. It's kind of a safety check here.
Is sbatch the same thing as qsub from the previous system?
The syntax is different, but the mechanism is essentially the same. So Slurm is the name of the scheduler. The old scheduler was called Moab and had Torque underneath. Slurm has a somewhat odd way of naming some certain things. The thing that isn't odd is a job. A job is a job. It's a piece of work that you schedule, and a node is a node. But when you have an MPI run, MPI application, if you want a bunch of MPI tasks that work together, I would call that an MPI process. If you're using MPI, that's what you're used to. Slurm calls that a task. And so when it matters because when you're asking for resources, you have to say how many tasks you want, or either total tasks or tasks per node. Okay, let's jump to threads. If you want threads, if you have a threaded application, so an application that uses multiple cores on the same machine, that can be useful. Slurm doesn't really have a name for that. It doesn't really know what to do with that, but it counts number of CPUs. But these CPUs are not real CPUs. They are the logical CPUs. I already said there's 40 cores on a node, but the operating system thinks there's 80. It's been tricked. Slurm also thinks that there are 80. It can be useful sometimes to use 80 processes at the same time rather than 40. It makes it a little faster. So it's those sort of virtual CPUs that Slurm counts. So the number of CPUs per task is the number of threads per MPI process. Okay. If you want to know what I'm really using, Slurm calls that a billing. So you get billed for how many cores you use. You don't really get a bill, but that's basically how it accounts for it. And so it knows that every node is built for 40 cores. So if you ever looked into, there's some Slurm commands like SACCT, account, that shows you your jobs and how many nodes you use and how many cores. If you look at the billing field, it'll actually give you the real numbers. So it's good to know that the real stuff is under billing. So one of the things that it matters for is that a lot of these things don't matter all that much unless you're running, say, hybrid MPI code with threads, or you're using a threaded application. If you're using something threaded, you want to ask for CPUs and not tasks, because tasks are MPI. If you're running MPI, you want to ask for tasks, not for CPU. So I have two examples, one for MPI and one for OpenMP, just to make that distinction. We're scheduling by node, I already said that. They're yours, make sure you use all of them. We have this thing called hyperthreading, so that's the cheat of having the nodes think that they have 80 cores, but they really have 40. We had it on the GPC as well, but 80 versus 40 doesn't give you 2 times as fast because they're sharing the same cores, but in a clever way. Typically, though, if you're running 80 things at the same time rather than 40 on the same node, you get somewhere between 5 and 10% speed up, which is free. So you might as well use that. But when you're starting, you typically just go, okay, there's 40 cores, I'm running 40 things. Keep things simple. My timings will make sense because, yeah. So hyperthreading is usually an optimization you do at the end. You have your job, it's running, you know it's working, you've tested it, now you're going to try it. It's much faster with, or any faster with hyperthreading. So here's an example script for OpenMP. So if you've seen submitting scripts in the old system, you know you had these pound somethings. They were PBS before, now they're called SBatch, and then there are a number of parameters. So the most important one is the number of nodes you're asking and the time. So I'm asking for one, I think this is 1 hour, yeah, 1 hour, and 1 node. Now this is an OpenMP, so it's a threaded application. I have to specify, or I should better specify, how many CPUs I want. And CPUs are threads for the purpose of Slurm. But then I still have to set my OMP num threads. So that's a specific variable that you use for OpenMP programming. A few other things. You want to set, if you don't set mail type, you don't get any mail automatically from failed jobs. You might not want that. But if you want your failed jobs to come to give you an email, you can say that by mail type fail. If you want your mail, if you want to mail for anything, like your job starts, you want to mail, your job ends, you want mail, you can say mail type is all, and it uses the whatever email address you associated with your CC account. There is a way to specify another one as well, but okay. We can specify where the output goes, and it has a few placeholders. %J is the number of the job, so that every time I run it again, it goes into a different file. And we can give it a name.
So it creates files for you, the output files?
It creates, sorry?
Like it generates files for every job?
Yeah, so you get, so whatever, and that file is whatever this script would produce on screen if you ran it on the login node.
Mm-hmm.
It's probably better to have explicit files in here, right, rather than count on the output to work, but it should go somewhere. And this is the one that you want to make sure that this one goes to scratch, because if you specify something that somehow defaults to something at home, it won't work. It will actually tell you, no, you can't write to home, which is confusing, because of course you can write to home, but not in the job.
Mm-hmm.
You have to reload your modules. That's another thing that is important. Gives you a record as well, so it's not so bad. You want to know what modules you are loading when you're running this job, so you have to load them again. Other than that, so this part is green. Top part is read by the scheduler. As far as the execution is concerned, when the script is run, these are just commands, so it doesn't do anything else anymore. But the scheduler picks these up, it goes and looks for a job for an hour and sees if there's a hole in, and there's usually not a hole in the schedule, so it puts it in a list and it figures out a priority and it orders them according to priority, and the top one goes first. I think I got that. With MPI, it's pretty much the same idea, except now instead of asking for CPUs, you ask for tasks. And the nice thing about MPI is that you can run in parallel over several nodes. So I've asked for 2 nodes here. Output is there, mail type is there. Oh, I didn't mention this yet. The submitter kind of says it already, but it's the directory from which you submit it. So you could be, this depends on your workflow. You could have your job scripts have the absolute path of where your job runs. So you could do CD. If you don't say anything, you will be in your home directory. Again, that's no use because you can't write there. So you want to do some sort of CD in the beginning anyway. But if you want to CD to the directory where you typed SBatch on the Lego node, you can. That is encoded in this slurm submit there. So you submit from some directory, some subdirectory in your Scratch on a login node, and then when this runs on one of the compute nodes, it will CD to that directory that you submitted from. And that's usually the way you want to run. And then you can have everything that is to do with that job in that one directory. And if you have to run it again, you just copy the directory to a new directory, and you don't have to change anything. You just submit that.
So in the previous example, number of CPUs was like number of cores on the node?
Yes, so we'll always have to do something with the number of cores. So this is the number of cores on a node, but in this case I want to use them as threads.
Okay.
So that's why I call them CPUs. And it'll probably work if I do it wrong, but not always. So CPUs are threads, tasks are MPI processes,
Okay.
or just processes you spawn yourself. Like if you're doing any of the parallel packages in R or Python, they spawn processes. So tasks and processes are essentially the same.
Wait, I don't understand what MPI process is.
So an MPI process is started with MPI run. And so there are different processes that work on the same system. Basically, you run the same program,
Yeah,
say,
on different cores.
right, on different cores. And so each of them is called a process. Right? It would make sense to call them tasks, fine, but some people call tasks threads. And so the whole thing is very confusing.
So each MPI process can use multiple cores as well?
It could, yes. And then you do some combination of these where you'd have a certain number of CPUs per task. So you use 2 threads in a task, you make this 2, and then probably your number of tasks per node is only 20. And so you could play those games. And if you have a hybrid code that can do that, then it can really make a difference in what's the optimal division. But yeah. Here again. MPI run, that's also kind of nice, will pick up on the number of tasks, so you don't really have to specify it. You can still say -n80, it'll still work. It's okay. I don't think you can give more than the number of tasks you asked for. that.
Mhm.
It sort of says, no, you only ask for so many, so you want to get these numbers right.
And so like you use threads if you want to share memory amongst the different processes.
That's right. Yeah.
But don't the cores already share memory? They're on the same node.
They do, but in the API mode, they don't use that. So they actually don't see their processes by default shield
Yeah,
each
but
other
in
memory.
OpenMP you use threads.
Yes. So if you use OpenMP,
Mhm.
they can see each other's memory, but you launch them as a single application. Right? So you just launch one thing, and that then
Okay.
spawns the other threads. And API is the opposite. This API run actually starts 80 copies of MPI,
Oh, okay.
for example, and then early on in their run, they figure out, oh, we all belong to the same group. Okay, so once it's in the queue, you can kind of look at what's happening. You can type SQ to give you the whole queue. That's a long list. You probably want to do something like SQ-U and your username, then you just see your jobs. It'll give you if they're running, if they're pending. It'll give them if they're completed, but only for a split second, and then it'll leave them out. Maybe not a split second, maybe a minute or so. If you want to know exactly how one of your jobs is doing, when you submit it, you get a job ID. It spits it out to the screen. You can use that job ID to figure out exactly that node. You can ask Slurm to give you an estimate on when your job will start. That's nice as a really rough estimate, but it's no guarantee in any sort of way because it assumes that nobody else is going to submit a job after you. And the jobs that are submitted after you do matter because they might have a higher priority. So it's not a really, it gives you more of an estimate of how busy it is on the system than really when your job will run. It's just an order of magnitude estimate maybe. Once it's running, you can get a view of what your job is doing on the different nodes or a single node using job perf. We had this command on GPC as well. Job perf, job ID will actually query each of the nodes that your job is on and tell you how much CPU it's using, how much memory, how much RAM disk, and also what it's running. So if you're running your MPI task, you would expect to see 40 of the same task running on each of the nodes. And if you don't see that, something is obviously wrong. You can cancel the job with scancel. You can get some information on the availability of nodes with sinfo. And you can get some accounting information with SACCT on your recent jobs. So if you just type that, you just get your jobs, and it actually will tell you yet again how much memory they were using, how many cores, some information like that. But so this is nice on the command line. But then we also have a website, and we're going to talk about that also in this snug that is right after this, so the user group meeting. This website, let's go there and show you. So if you just log in, if you haven't logged in, it will just show you the status of Niagara. How many of the nodes are busy computing? So that's a nice 89%. It'll give you how full Scratch is. We're pretty good here. The burst buffer is underused. If you need burst buffer, just ask. It'll also give you how many jobs are in the queue, so how many are running, how many are in the queue, how long they will, on average, still be running for. So in 12 hours, if there were no jobs waiting, pretty much everything would be done. And how many hours are pretty much asked for. This gives you an idea of the oversubscription of this system. But again, a lot of these are just opportunistic. I'm going to put these jobs in the queue, and I hope they'll probably run out of priority. So don't despair too much with this. This is a work in progress, so we'll talk a little bit about it later, but it tells you what's going on the login nodes, and then has some links. But most importantly, if you sign in, let me sign in with my password. You can see your jobs. So you can go to jobs, and because it's me, I'll see all the jobs, but you would by default just see your jobs. You can see what I've run in the past, and how I ran some things 2 weeks ago apparently. I hope these were short tests. And if I click on any of them, let's do something that's a little longer. Like this one. It would give me how much CPU is used. This is such a short run that I only have one sample point. It usually shows your script, don't save the password, and your environment as well. Yeah, CPU usage, you can get file reads, memory, a whole bunch of other performances. So it's good, especially if you've just done, say, launch a test job, see how things were running. The CPU should be near 100%, or the memory available should be close to 0. So that if you want to max something out, then it's efficient. So that's nice, and it's still kind of in progress. It's still called alpha, but it does work, and it's nice. So we can monitor. So that's basically the whole life of the system, right? So log in nodes, you prepare your job, you compile, you submit them, you look at them, make sure they run well. So a few tips to end on data management, and it's something you have to be more aware of at large scale than at small scale. When you're computing on your own desktop, it hardly matters what you do with your disk or how you save things, as long as it makes sense to you, right? That's not true on a large shared parallel file system. And our parallel file system is called GPFS, so we'll often say GPFS, or we'll blame GPFS for something. It's a shared file system that all the nodes see. That means that if I write a file from node 10, all the other nodes can suddenly see that file, right? And if they both want to write to that file, this parallel file system will somehow figure out who can do this first, so that the file is not corrupt or anything like that. So that means that it is possible to sort of slow down this system by doing complicated things. And complicated things here means things that are hard for a shared system to figure out who's doing what. So you do lots of little writes to the same files with the same directory from many nodes. It's going to be tough for the file system. It's really designed for large streaming data. So not streaming as in video, actually you could use it for that. But say you have an application, it has a lot of data in memory, and it sort of wants to dump that to disk as one big chunk. It's really good at that. It's good bandwidth. I can do that from different nodes to different systems. It'll use all of its bandwidth. That's great. What it can't do very well is small reads and writes. So okay, I want to create a little file here. Now delete it. Now or I write lots of files in the same directory. It's not really good at small stuff. Burst buffer is better for that. And the reason this matters so much is that when you do sort of this kind of bad behavior, when you have a few dozen jobs, they're all doing rapid I/O on the file system, the file system becomes sluggish because it's busy figuring out what to do with all these files. So the metadata becomes important. This is true for all parallel file systems. Similar things can go wrong on Graham and Cedar, where they have Lustre instead of GPFS. Many file systems just leads to poor performance. It's also kind of a maintenance nightmare. Like if you're running on your own desktop and you have a few thousand files, maybe you can manage. But now you go to Supercomputer because you have 1,000 of these cases. Now you have 10 million files, and you'll never look at 10 million files, right? It's the way you structured your data, but for you, they're not files that you are going to look at. So if you ever have to restructure that by hand, it's just a nightmare. You want to try and not do that. So avoid that. It'll make things faster, make things better for you. If you have numerical data, don't write it out as text. That wastes space and time. And just, yeah, keep that in mind. Keep in mind that this is a shared system that is good at big reads and writes, big files, and not lots of little files. Okay, so that's pretty much it. If you want more information, a quick start rehashes much of this. You want to see some nice stories about SciNet, you can go to our main page. The status of the systems is most accurately kept at the the wiki site that also hosts the Quick Start. If you want to take more of our training, go to the courses website. And if you need support, Niagara at computercanada.ca or the old